Traders, a little bit of a trigger warning before today's show. I had the distinct pleasure of speaking with Samir Varma in this show and the next, a two-part series. Samir is one of my favourite guests, I've got to admit. He is a quantitative hedge fund manager, of course, but he's also a quantum physicist, an inventor, an author, a deep thinker, and interest in AI and other things. It was too good an opportunity for me to delve into a few subjects with him that were not specifically trading, i.e. the quantum physics in particular. So if trading is your thing and that's all you've got time for and you don't have time for anything else, please skip this show. I will not be offended. Leave a comment below. Tell me that if I ever do this again, you're unsubscribed for life. I get it, no problems. I'd like to hear what people do think. But in my initial chat with Samir, I got into all this other stuff. I wanted to pick his brain. We talked about everything from quantum physics to AI to free will and determinism, Asimov's 3 laws of robotics. And yes, we touch on the trading in the end as we get into the second part, which is to come, which you will not want to miss. A fantastic episode talking about systematic trading, his methods, principles, style, his way of thinking is coming up in part 2. So whatever you do, don't miss that. I hope you enjoy this show. I could not but release it. It's just too interesting for those who will enjoy some of the chit-chat about quantum mechanics. The markets are complex adaptive systems. So this episode's owed to you, Rich Brennan, my co-host from the earlier episodes. I hope you enjoy it. And don't forget, the Algo Collective and Algo Academy are open. We are live. Algo Collective is our private members area, a collection of traders all working together. There's lots of content to come. We've only just opened. There's already a lot going on in there, which is fantastic. But look, there's a 3-day trial. Poke your head in, have a look. There's nothing to lose. Algo Academy, we have our crypto trading course live now. That's a very extensive course, 10 plus hours, plenty of video, code, you name it, multiple strategies and edges. Very interesting course. Of course, we have Tom Stark with Python for Quant's courses as well. Very good stuff. I'm here to help you. If you're a trader in transition, looking to have your best year ever, then I would love to have something to do with that. I hope we can do that together. So yeah, come in, have a look, ask me any questions. I really appreciate you subscribing to this channel and subscribing on the website or on Substack and having a poke around. It all really helps, especially now as we're transitioning into trying to deliver more meaningful content, partnering with industry bests, not just nobodies, so that you've got some really quality sources of systematic trading education. Really appreciate all your support and your help. Please get in contact with any questions. Here's the show.
Welcome to the Algorithmic Advantage. We're here to expand the toolkit of the quant trading community and introduce investors to the many advantages of systematic trading. Our goal is to educate and inspire as we embark on a captivating journey into the vast knowledge and experience of leading portfolio managers and other experts in the field.
Yes, I found out about you through the trading circles. Obviously, we need to get into that at some point. Obviously, it's nice to, I would say, like if I was going to hazard a guess at my audience, like I would say, let's say 25% of them are probably somewhat familiar with some basic principles of quantum mechanics because they're sciencey minded, they're data scientists, they're quant traders. The vast majority of people, not so much. You've also got an interest in AI, which again, I mean, not only does the whole world have an interest in AI, but again, particularly, I guess, quant traders, systematic traders, first to use these tools, they're developers, they're computer science people, and we're trying to look for every bit of help we can to get edges in the market. And then you've got the trading. So, I was happy to start with the quantum mechanics and see how that might feed into your trading, if at all, like what influences
to me, it's all the same thing.
Which is fantastic. So there's a philosophical side to you, obviously, as well. I did just buy your book just on the Kindle. Yeah, and I've recommended it to someone else who's just bought it as well. So there we go. The podcast has launched 2 sales of the book. but I haven't really got into it yet. So looking forward to that, which is also why I thought we might talk again after this, but we'll see how this goes. I mean, would love to keep talking.
Happy to talk anytime, honestly.
Yeah, wonderful. So, like, just starting off in the quantum mechanics, one of the things I sort of thought about was it might be nice to give a bit of a layman's introduction to, you know, the core principles that we uncover in quantum mechanics, and obviously particularly as they kind of start to relate to trading, just in terms of dealing with probabilities and uncertainty. So some of those key aspects, and then maybe to even ask for an explanation of, say, the double slit experiment, which always blows people's minds if they haven't heard it before, and gives some nice foundation, or maybe another experiment that would give some kind of insight into, you know, how these things have begun to be thought about, some of the history. But yeah, could you give maybe some kind of introductory statement about, you know, quantum mechanics and what we've discovered there?
Yes, so that's a great question. And in fact, I start my book, which is called The Science of Free Will, with an explanation of quantum mechanics, specifically actually the superset of quantum mechanics called quantum field theory. And the reason is that at the end of the day, every single thing in the universe is a field. And I'll explain what a field is in a second. But the important point having to do with the fact that everything is a field is that fields have equations. Those equations can be written down. We know what they are, and we know how they evolve. And you know, we know that they're right to 14 decimal places, as I said earlier. So we know that we're not making this stuff up. It's actually scientifically valid. And the interesting thing about that is that the very fact that the field exists explains to you all essentially the mystery of quantum mechanics. So what is the mystery of quantum mechanics? The mystery of quantum mechanics is, supposing you take, let's say, a sheet of paper, you know, like this, and you cut two slits in it, very, very close to each other. Now, if you fire something through those slits, let's say light, because the slits are close together, you expect that there'll be an interference pattern behind the slits. And you can see that interference pattern. Now, if light was a wave, this is not at all surprising, because you throw one rock into a pond, you throw another rock into a pond, the two sets of waves intersect in various places. In some places they reinforce, in some places they cancel. You get an interference pattern. Not a big surprise. But what Einstein showed in 1905, by the way, he won his Nobel Prize for this, not for the relativity, which is amazing. He showed this thing called the photoelectric effect, which is the same thing that powers solar cells. And that is that when light shines on a specific material, what comes out of the material are actually individual objects or things that you can measure individually, and we call those things photons. So photons are the individual particles of light. And the mystery of quantum mechanics is that even if you fire light at these slits, where it's one photon going through the slit at a time, and you know it's one photon going through the slit at a time, as long as both slits are open and you don't measure which slit the photon went through, you will get an interference pattern at the other side. And so then you get all sorts of woo-woo interpretations of quantum mechanics. Oh, the photon went through both slits. Oh, this has to do with consciousness, or this has to do with the observer. It has to do with this, it has to do with that. But in fact, it's much less of a mystery than you might think. And the reason is that the photon doesn't actually, strictly speaking, exist. What exists is a photon field. A field is basically the statement that at every point in space and time, you attach a collection of numbers. So it's not one number, it's not two numbers, it's a collection of numbers. That collection of numbers at every point in space-time is the state of the field at every point in space-time. And all that's happening is that when you say photon, what you're saying is that the field is no longer in its unexcited state. It's no longer in what's called technically the ground state. It's in a state that is one level up from its ground state, and we're calling that state that's one level up one photon. And so if you have more photons, then it's moving into a different excitation. And because it's a field, because a field is defined at all points in space and all points in time, always, it's not a surprise that a field passing through one slit is interfering with a field that is passing through the other slit. Or to put it even more accurately, the same field is actually passing through both slits. So if both slits are open, it will interfere with itself because it's the same field. But if only one slit is open, it has nothing to interfere with, so it doesn't interfere. That's really what's going on in the double slit experiment. And that's really what's going on with essentially all of the mysteries of quantum mechanics. All of them are solved by going to the superset of quantum mechanics, which is quantum field theory, which is treating everything as a field. That's the key point. And that even the philosophical problems, a lot of the woo-woo stuff that people like to say in popular physics is not valid for that reason. And I go through this in my book. I actually explain in my book what a field is, why you should care, what that has to do with free will, and then, of course, what that has to do with AI.
A silly question. How sure are we? I mean, obviously, we are so unsure about so many things. This is a philosophical question. We're obviously measuring things that require tools that are so advanced, they're almost, I guess, I'm stabbing in the dark, but measuring impacts, like it's not like we can observe these things naturally and simply. We've got really complex ways of setting these experiments up. Again, it's a newbie question, so forgive me, but philosophically, like, is this all proven now? Are we sure? Do we know this stuff? Can we say that we know it? Are we happy with where we're at in the field, or are we still speculating about some of this and are the tools getting in our way, so to speak, when we are trying to measure these things?
Very good question. So the answer to that is that any of the physics that underlies biology is already known and has been for 75 years. And it's known, as I said, to like 14 decimal places in some cases and 8 and 9 in other cases. The places where there is some uncertainty is at very, very high energies. And those energies really only obtained at the very early stages of the universe. And depending on who you talk about and how you ask the question and so on, somewhere between 10 to the minus 20 and 10 to the minus 40 seconds after the Big Bang. That's how far back you have to go before the physics starts to break down and you're no longer sure of anything. But so when you say 10 to the minus 20, that's 0.0, 20 times. So that's 20 zeros, 1 of a second. So we've been able to go back that far and that far back where we are sure we know what we're talking about, because we can do the experiments and the experiments consistently come back giving us answers that make sense. At the very highest energies, yes, there are puzzles, and that's what people are trying to solve at places like the Large Hadron Collider, that is CERN in Geneva and so on. But at low energies, biological energies, there are no mysteries. From the physics, none whatsoever. Now, how the physics turns into chemistry and the chemistry turns into biology, that's a different question altogether. Just because you know the fundamental equation doesn't mean you can calculate anything from it. That's a completely separate question. And that, in fact, is the nature of free will, by the way. The nature of free will is the fact that even though you know the equation, you don't know what the equation's result is going to be until you just follow and see what happens.
Well, okay, so when you say we are sure, like all the experiments evidence that our formulae and our understanding of quantum mechanics is on target, is there a Nobel Prize waiting for the person who can just explain it in a way that makes sense, though? Where's the gap that it's so ethereal?
The gap is that the mathematics is perfectly well defined. We just don't know how to convert the mathematics to English. And so then we reach for analogies. And I personally don't like analogies, and I don't like analogies because they create the illusion of understanding without actually producing understanding. And so I like to stick to the facts as much as possible, even if that's, in a sense, more puzzling, because then you as a logical person, if the other person is just giving you the facts, can at least reason through the facts to some extent. Whereas if all you're given is analogies, then you have no idea how far you can push them. That, I think, is the problem, is that in popular science books in particular, publishers like physicists and others to make up these analogies and then just wrong. Like, I don't know if you've ever heard of or been interested in the Higgs boson. There was a big fuss about 10 years ago, right? So some people like to, not some people. The Higgs boson is the thing that gives mass to everything in the universe. The way it's always explained is that it is as if, particles are massless, but they're moving through molasses. And because they're moving through molasses and the molasses is the Higgs field, it gives them mass. But actually, if you look at the math, that's just wrong. And there's an excellent physicist called Matt Strassler who wrote a book, I think, called Waves on an Impossible Sea, where he got so annoyed at this entire analogy that he said, I'm going to write an entire book to explain to you what's actually going on. And it has to do with vibration modes and the way things, essentially the way waves wave and how those things add up and so on. It's much more technical. It's nothing to do with molasses and moving through liquid, because the instant you start thinking about that, you start to see problems with the analogy, which is why it should never have been used in the first place. But this was what happens with all of these physics analogies. They're terrible. I don't like them, so I refuse to use them.
Yeah, you're left wondering what might be exactly the assumptions underlying, and I guess that's where you can then become uncertain and unclear.
Exactly. So here's an interesting fact for you, or factoid, however we're going to think about it. We have done millions of experiments at this point that have to do with quantum mechanics. We have never had a single experiment ever, not one, that has contradicted quantum mechanics, which is incredible. I mean, there's no other scientific theory other than perhaps the general theory of relativity, which can say that, where you've never had an experiment that has been contrary.
So Einstein famously, took issue with quantum entanglement and so on. Did he resolve that later in life? Did he come around, or did he die a opponent? I don't know how that story ends.
He hated the philosophical implications of quantum mechanics, but he accepted the mathematics because he's a good physicist. So what he was trying, even to the very end of his life, was to try to find some mathematics that made him philosophically happy and yet was consistent with the mathematics of quantum mechanics as known at the time. Now, since then, we've gone a lot further. We now have, quantum field theory, which is already being developed at the time, but quantum field theory is a much bigger subject today, which you would not have known about. Anyway, at least not to this kind of detail. So did he make peace with it? No, not really, but he did accept it.
All the experiments, you said, so all the experiments have validated our understanding of quantum mechanics. What's this gap that lies for us, and why do we need to solve it to find this grand unified theory of the large and the small, as it were? Why do you think we're failing there?
Well, there's several questions there, and they're all very interesting. So the first question is, why do we care? The first order answer is because we're curious. We would like to know more about our universe. That really is the fundamental answer. The second order answer is that every time we found some new fundamental physics, it has eventually led to a giant increase in people's standard of living. So the first such thing was Michael Faraday and whoever was Michael Faraday's contemporary, I can't remember anymore, sorry, in the 1850s in the UK, when they discovered electricity and magnetism.
Not Tesla?
So at the time, the joke was, I think some prime minister came and asked him, well, sir, of what use is this demonstration? Because he'd just shown, a few clicks going across a wire or something like that. And he said, I don't know, Prime Minister, but I'm sure you'll find a way to tax it. That's the joke. But in fact, modern life would be impossible without electric power. But somebody had to figure out the physics behind it. So that's one example. A more recent example is that the same physics that Einstein figured out that powers cosmology and powers black holes and all of that stuff is the exact physics that is needed to make your iPhone work, believe it or not. And the reason is that your iPhone runs on GPS satellites. GPS satellites run on a precision timing system. The way they work is by triangulating signals and figuring out the difference in time from different satellites. That difference in time is affected by the general theory of relativity. And if we did not have the general theory of relativity, we could not do the calculation to anything like the accuracy we do, and you could be off by miles or more.
So we actually have to adjust time.
You have to adjust exactly. That minuscule effect on Earth scales, which is of course a giant effect of cosmological scales, actually affects our daily lives right now. So the point is, we don't know what will happen when we put together the theory of the very small, that's quantum mechanics, with the theory of the very big, which is general theory of relativity. But we'll have learned something important about the universe. And history suggests that whenever you learn something important about the universe, eventually it turns into a technology, an important technology usually.
So why don't the laws of gravity fit in with quantum mechanics?
Yes, that's a long-standing problem. The best way of thinking about it is that quantum mechanics requires the uncertainty principle. That is to say, you can't measure, let's say, the momentum of a particle and its position with perfect accuracy at the same time. That's what makes it quantum mechanical. Gravity has the exact opposite feature. You can measure anything as perfectly as you like at any time. And if you try to put the uncertainty principle into gravity, you end up with nonsensical infinities. And you end up with infinities of many infinities we can make go away. And we do that in quantum field theory all the time. But these infinities are so bad because gravity can interact with itself and does interact with itself, that we have absolutely no idea how to make them go away. So no one has a good clue. We have some ideas for how to do what's called quantum gravity. String theory is one potential way of doing it. Loop quantum gravity and various other things. I won't bore you with those other ways of doing it. These are all ways of trying to reconcile the uncertainty principle, as it were, that comes from quantum mechanics with something classical. We call something that's not quantum mechanical classical. So, which doesn't have any uncertainty in it.
Can we use the understanding that we have of quantum physics to explain everything else in life? Can it be used broadly?
In principle or in practice?
I'll let you decide. Let's say in principle.
Okay, in principle, yes. In fact, in principle, it explains everything. It must. Particularly in a biological and chemical scale, as I was saying earlier, it must. It has to. It has no choice. But in practice, no, because once you go past about 100 objects in quantum mechanics, like 100 wave functions, we don't have the computing power to compute past that.
Right.
So we then have to create effective science. And so basically all science that is not quantum mechanics is effective. That is to say, it's what happens when you conglomerate large things together, and we don't have the computing power to be able to predict them from first principles. So we have to create new science, as it were, which we could not have predicted from the principles, even though we know the principles exist. And now you could say, well, how do you know that the principles apply even at the level of, many millions of atoms as opposed to, 2, 3, 4, 5? And the reason is that we know that every atom is the same as every other atom, and we can prove that. And so therefore, it has no choice but to exist. So if it's true for one atom, it's true for 2, it's true for 3, it's true for 4, it's true for 20 billion. It doesn't matter. And we also know that these are the same atoms that exist across the universe, because we can look at spectra from stars and from galaxies. So they're the same atoms here as they are, billions of light years away. And of course, billions of light years means you're going back billions of light years into the past. So not only are they far away, they're also in the past. And we know that they're the same atoms then as they were here, because we can tell that from the spectra. So again, they're indivisible. They don't change. not indivisible. That's the wrong word. Unidentifiable. They're the same. You can't say this atom is different than that atom. They're the same atom.
Do black holes definitely exist also? I know this is some astronomy here, perhaps, but are we sure about black holes?
It depends on what you mean by the word definite. I would say the probability that they don't exist is under, my opinion, 1/1000%.
Right.
About 15 years ago, you could have said something different. You could have said, oh, I don't know, maybe 2-3% chance that they don't exist. Why do I say 1/1000%? Because we've already seen and calculated from general relativity what would happen when two black holes collide somewhere across the universe. They send out gravitational waves. We've detected those gravitational waves, and we found that their predictions exactly agree with the predictions of general relativity. So they must exist, because if they didn't, then we wouldn't see those gravitational waves. Now, you could argue, well, you didn't actually see that black hole from way across the universe. What if it was two just very heavy mass objects that banged into each other? Yes, but we know from other consistency conditions that objects of that size are going to, of that mass, are going to be black holes. Again, you don't have a choice. That's one of the things about fundamental physics. You because of the way it works, you can apply what are called consistency conditions, which is to say, if this is true over here, and then I can mathematically show that that implies, A, B, C, D, E, F, G, H, then H must be true too. And you find that from basically studying collisions of these black holes. And there's lots of them now. I think we detect one every 2 days or something at this point.
Oh, really?
Yeah. There's lots and lots and lots of these events. It's so common that they don't even talk about it anymore. Even though it's a remarkable achievement.
And I mean, my mind's just racing, so I'm just going to drop the questions as they come. Quantum computing, are we there yet? How far off are we? And also maybe just give me a bit of an explanation of quantum computing, and as much as you can. I mean, how does it work?
So, look, it's not a very satisfactory answer, I tell you that. A lot of what people are telling you is driven by commercial pressure.
Yeah.
And it's driven by two kinds of commercial pressure. It's driven by research pressure, because you have to get your grants funded. So you have to say encouraging things to get your money. And then if you're going to go to a venture capitalist and say, hey, give me some money, dude, I want to build a company, you have to say some encouraging things.
Something practical is going to come.
Exactly. So the problem with quantum computing is the following. And I'm neither skeptical nor not skeptical. I'm in the camp of, I don't know, man, show me.
Yeah.
But basically what's going on is that for reasons having to do with the way wave functions work and the way they add, when you run a quantum computer, you're not actually running one calculation. You're running a very large number of calculations all in parallel. So think of it as the ultimate parallel computing device. So what happens is you set your problem up in a certain configuration of very cold objects. Very cold because you don't want them to interfere with the rest of the universe. And you allow them then to interact and evolve in such a way that when they end, they will be in a configuration that is a solution to the problem that you are trying to solve. The issue with quantum computing is twofold. The first problem with quantum computing is that since you have to keep these things very cold, you have to stop them from interfering with the rest of the universe and so on and so forth. You get lots of errors as the computation is taking place. So the first problem is the error correction as the computation is taking place, because you've got to keep this stuff cold and isolated, and it's really, really difficult. The second problem is at the end, you've got a state, but it's not really technically speaking one state, right? We just did a parallel computation. So you also then need to have a way of picking out that final state in such a way that it gives you the answer to your problem. And there's some evidence and some argument as to whether the advantage gained in the parallelism this way is lost when you have to interpret the final state to get your solution back. So it may take a lot of computing just to figure out what the solution is that final state is telling you. Now, there are plenty of arguments about how there are special problems where that's not true, where essentially they simulated annealing and a few others. Again, I won't bore you with those, which will end up in a final state that's easy to interpret. That's true, but that's a very limited class of problems. It's not like a general purpose computer like we have in front of us right now that can run any algorithm and give us back an answer. So there are significant practical issues. How near we are to solving them, or even if they're theoretically intractable, I don't know. It's very hard for me to tell, and I don't also have the energy to go through the hype. So I don't know.
Yeah.
I'll see it when I see it.
We'll see it when we see it. How does all of this thinking about quantum mechanics get you thinking about determinism and free will? And again, I'm obviously an amateur, less than an amateur. I know nothing. But when I think of the word determinism and things being determined, and I compare and contrast that to the understanding of quantum mechanics where everything exists in a state of probability and uncertainty, how do we get determined and determinism out of this uncertainty anyway?
Yes, good question. So that's one of the things that I talk about in my book at length. So here is the point. The equations that underlie quantum mechanics, i.e. quantum field theory, are completely deterministic. We know them. We wrote down the equations for quantum electrodynamics, which is the theory of ordinary light and matter in the 1950s. Those agree to 14 decimal places. We then wrote down the equations that have to do the weak interaction, 20 years later. Those agree to some crazy number of decimal places. And then we wrote down the equations that have to do the strong nuclear force, which is the force that holds the nucleus of the atom together, protons and neutrons, called quantum chromodynamics. And that was in the 1970s, 1980s, and 1990s. All those predictions have been made. All those predictions have come out. All those predictions are correct. All of them, every time we try to test it, other than a few discrepancies, very high energies, we get the right result every single time. Okay. So that means that, that's point one. Point two, you are made up of atoms. The atoms are made up of electrons, protons, and neutrons. Protons and neutrons are made up of quarks. And as I just said, we have the theory of quarks called quantum chromodynamics. We have the theory of electrons and photons, which is quantum electrodynamics. You put it all together, it's called the standard model of particle physics. It means that the standard model of particle physics applies to you as a person. It applies to this computer, it applies to this microphone, it applies to everything, because everything's made of that same stuff. So if everything is made of the same stuff, and that stuff is following a mathematical equation, and we know what that mathematical equation is, we've written down already, then the question becomes, in what sense are you different than a machine? Because the mathematics is deterministic. It is what it is. You write down the equation, you plug a time t into it. At some point in the future, you'll know the configuration of the particles at that time t in the future. And this sounds like a philosophical question, and it is, but it has deep practical significance, even for trading, by the way. And the deep practical significance is, what is free will then in that case, if we're all made up of fundamental particles that are following a mathematical equation? And the answer is, despite the fact that we are all following a mathematical equation, because there are 10 to the 27, one followed by 27 zeros, atoms in our body, each of which contain a multitude of particles, the chance of being able to predict what you are going to do in the future is basically zero. Not basically, it is zero. It's not going to happen. And it's not going to happen for three different reasons, which I get into in the book, but that's not relevant to the current discussion. But the fact that you cannot know what anyone, including yourself, is going to do until you do it is free will. Now, the reason this is deeply practical is that when you take that definition and you apply it to the conversation du jour, i.e. AI, it turns out that AI has the precise same free will that we do. We don't know what the outputs of the AI are going to be before the AI gives us the outputs. And furthermore, because it's so complicated, we have no hope of ever knowing what it's going to output. And furthermore, and this is where it gets interesting for trading, is that if we did know what the AI's output was going to be, we wouldn't need it. We would replace it with the algorithm that produced the output. So this is a phenomenon that was named in the 1980s by Stephen Wolfram, the famous scientist. It's called computational irreducibility. It's a big mouthful, but it's a very simple concept. The simple concept is that imagine that there's a set of rules. And let's imagine these rules are arbitrarily simple, not complicated, simple. So, things like, here are 3 squares, 2 of them are black, on the 2 sides, and 1 is white in the middle. If you see a configuration of, black, white, black, the next one is black. That kind of incredibly simple rule. That kind of rule that I'm just talking about right now is called a cellular automaton. That's its name. But there are other simple rules that are also possible. These are rules that I like to say a 5-year-old can follow. The interesting thing about it is that you can show that the output of many of these rules that, as I just said, are so simple that a 5-year-old can follow them, is so arbitrarily complicated that it is not possible. Forget in practice, it's not even possible in theory to predict what the output of that rule is going to be, except to just run the rule and see what the output is. And so that is what I say in my book is in fact the nature of free will. Free will is exactly that statement. It doesn't even matter how simple the rules are. If the rules are computationally irreducible, there is nothing that you can do to shortcut to the result other than to wait for the result to happen. I.e., you have to live your life to know what your life is going to turn out to be.
And
or
so
to put it another way, you and I have to have this conversation to know what is going to happen in the conversation.
So practically speaking, for us, there's no practical difference. Anyway, it becomes a philosophical debate. We've still got to live our life and, quote unquote, make the decisions and be held accountable, could I say?
Yes, that's correct. And so that's right. And so now taking it back to trading for a minute,
We've got to get there eventually.
Exactly. So the issue with trading is something that I'm trying to get my colleagues to focus on for a long time, but a lot of people don't really get this point viscerally. If you create an autonomous trading agent, the more you constrain that agent, the less useful it's going to be. And that must be true because in the limit that you constrain it completely, you already know what its output is going to be. So by definition, you have to give it at least some quantity of free will to make a decision, because if you didn't, then it's worthless.
It's not using what you've made it for. You've given it that ability.
Exactly. That's right. So if you don't know what its output is going to be, then you have the problem that, as like happens with every trader, it starts to lose money. Right? What do you do now? Do you turn it off? Or do you keep trading it? Or do you cut its allocation? What do you do? And the problem is that, as with human traders, right? You can talk to them, but that's not terribly satisfactory, generally speaking. You don't know whether it's because the AI has lost its edge, whatever its edge was, or it's no longer in sync with the markets or whatever else is going on, or because it was just lucky in the first place. You don't know. And so what's going to happen is...
Just like with a human trader.
Just like with a human trader. You're exactly right. And so what happens to human traders, I've experienced this, as I'm sure you have, and your viewers, I'm sure, have, particularly those that are traders. You go through a losing patch, people take money out, and then as soon as they start to take significant quantities of money out, that's when you turn around and start making money again. And this has happened to me more times than I would care to even talk about. But it's so common, and the reason is that you have the principal agent problem, right? The principal who has the money doesn't know about the agent's ability except by looking to see what the result is. Financial markets are incredibly noisy. So you can have a bad streak, but it doesn't mean you're a bad trader. And it's the same problem. It's the exact same problem. And so, when I talk to hedge funds and others, and I try to, explain to them that this is an issue, you guys are running headlong into, developing AI and putting AI in and so on and so forth. You guys need to really think about its interpretability. What are you going to do when it doesn't work? It's hopeless.
No idea.
Essentially, everybody, because I guess investors want to invest in AI, so people are taking in the money and asking questions later. That just seems to be how it works. But it's a real problem. I haven't heard a single solution to it. I've heard some sort of airy hand waving, which you can get into if you want, about Markov chains and things like that. But I mean, no, unimpressive. But that's the financial services industry, as you well know. It's more marketing than it is anything else.
What about just perhaps at a more traditional level, like a machine learning level, or even just using some of the basic tools of AI to do reviews of our trading and our data, looking at our output, getting it to make suggestions. Maybe it comes up with a novel suggestion. So using it as a sidekick, we take it on board what it says. We either regard or disregard it. I guess this is one way it's being used at the moment. Running a model, okay, analyze my model, rerun the model, tell me what you think could be wrong, or why it had this drawdown in that time, and it's got access to a lot of information, and it can run things quickly. So it's an extra tool, it's an extra colleague. Is that something you've been investigating or using, AI for in trading at all?
Yes. Okay. So what you're talking about there, you're talking about two different things there, both of which are very valuable. The first, you're talking about a decision support system, basically a way of compressing a lot of information so that the human in charge of the money can now look at that information and try to make a decision. That's a decision support system. That's great. AI is fantastic at it, which is why, of course, you hire lots and lots of human analysts, that write your report. You're the portfolio manager. You read the reports. You decide what you want to do with them. Yeah, absolutely. It's great at that. The second thing that you're talking about there is having it help you write your code, write your back tests, check your back tests, also check that that your logic is sound, that you haven't made any errors, or you don't have any bugs. And then related to that is you can even tell it, listen, I have the following idea. Here's my code base, implement it. And then you can check the implementation. That's all great too. It's fantastic for that. I use it myself all the time. But those are not, at least when I talk to a lot of the people that are out there, that's not the hypey stuff. The hypey stuff is AI is autonomous, and it's going to make decisions, and it's going to replace portfolio managers, and it's going to run on its own, and all this other stuff. And that's when I think it gets a little bit silly, because until the AI itself has its own money to invest, which, by the way, is not, I think, quite as far away or far-fetched as you might think, I think that problem of interpretability is always going to be there. And the second issue related to that is that if you then go talk to an AI when it's losing money and you say, hey, dude, why did you lose money? Right? It'll give you an answer, just like a human will give you an answer. But is the answer true? You have no way of knowing.
Yeah.
Principal agent problem.
I mean, I love the idea of thinking that an AI could be trading its own money and trying to rectify itself when it's losing money. But I would have serious questions around how we would ever be able to motivate the AI to care as much about money as we do. Does it know that its own life is on the line if it has a continuous losing streak? Does it understand the depth of a blow-up risk?
Yes. So let me give you a scenario. This is tongue-in-cheek, but it's meant to illustrate a point. So imagine that there's a bot, and the bot is very good at telling jokes. It's very funny. And let's say it now opens up an account on X, and it starts to tell really funny jokes, and asks for subscriptions. People sign up, and people pay the bot in whatever currency X has at the moment. They're releasing their own soon. Okay. Now the bot is running in a way autonomously because it's telling jokes and it's collecting money for the jokes that it's telling. It can now take that money and it can invest it because it's all crypto. It can convert one crypto to another crypto, whatever it wants to do in the blockchain. And it can trade that if it wants to. So now you've got a fully closed loop. The bot is earning a living. It's using that living to pay for its own computing and whatever else it needs to live.
Paying the rent.
And then it's investing, whatever its surplus is, the same way a human would. So now you've got a situation where there's a bot that is actually investing its own money. It's autonomous. It's genuinely autonomous. And that could happen today, actually, if somebody wanted to get it going.
I know, but does it care, Samir? Like, does it care if it all fails? Does it care as much as we
Doesn't
do?
it? If it knows that it's going to get shut off if it doesn't make money?
Well, how far away are we from AGI? Are you a proponent that you think this is imminent, or this is coming, or not at all?
I'll tell you the problem with AGI. Every time we find something that seems to work really well, we change the goalposts as to what AGI is. So do you remember the old Turing test?
Mm-hmm.
The old Turing test was, you sit two people at a computer. At the back end of the computer is, a computer program. If the computer program can prove to somebody sitting in front of the computer that's human by just chatting with it, well, then that's AGI. Well, we passed that a long time ago.
Yeah.
Right. I mean, now we've got AI, particularly ChatGPT 5.4, that's solving very hard mathematical theorems. It's pushing ahead in frontiers of particle physics. It's actually done some research recently that no physicist knew how to do. It's helping with all kinds of other scientific research. There was a story out of Australia, I don't know if it's true or false, about the guy that used ChatGPT to construct a vaccine for his dog that had cancer. And the dog was cured from this vaccine that he created using ChatGPT. Now, I don't know if that's true or false. I saw some things saying later, well, yes, but it's exaggerated, but it is sort of true.
It was actually his kangaroo, yeah.
Oh, okay. So, okay. All right.
Yeah, I haven't heard of it.
But the fact is, it's already there in some sense. So is that AGI? So I think that part of the problem is that since we're all flesh and blood, we don't want to believe that there's another intelligence that can be non-flesh and blood, but is also intelligent. And so, in my opinion, there are two things that are salient here. The first salient thing, because I'm a physicist, is, look, the AI is running on the same substrate, the same rules, electrons, protons, and neutrons as you. So there's no physical reason that says it can't be intelligent. If you're going to claim it can't be intelligent, then you're basically taking this ghost outside the machine view, which is most unscientific. But if you want to do that, you can do that, where there's something that inhabits humans that is different somehow than just atoms. The fact that we can never find it and there's no experiment that shows it to be there doesn't seem to bother people that propose this view, but that's what they say. Okay, so that's one thing to think about. The second thing to think about is to think about the history of animal rights, right? I mean, it took us forever to even concede that animals feel pain. It took us forever to concede that elephants grieve, other elephants that have died. It took us forever to concede that, dolphins are intelligent, etc., etc. So I think that what's going to happen is what always happens with these things is it's sociology. And it's just as we get used to it, we will sort of think less and less and less about it. And eventually we'll just say, well, that's how it is. And then somebody will say, well, is that AGI? And everybody will shrug and say, I don't know, but it's pretty good. That's my guess. So is it AGI? I don't know. Depends how you want to define AGI.
Yeah, it depends how you define intelligence, doesn't it?
Yeah, I think it is personally. I think it's amazing.
I want to just quickly respond to I'm just the interviewer. I try to keep my opinion out of it. But just in terms of the ghost in the machine, obviously there's a long history of philosophy from both sides of the fence, if you like, from a materialist and a spiritual. There's been a long spiritual religious discussion for a very long time. And I think the thought that comes to mind is that, I'm the same atoms as the computer in front of me. I'm even more similar to a version of myself that's dead. But the dead version of me with all the same atoms doesn't have much free will. There's some event, the more spiritual code of thought would still probably suggest that there's something going on with my atoms that we haven't yet defined, i.e. life. And we've certainly never really brought anyone to life, even if I've died, 5 minutes ago. So
okay. Actually, that's another fantastic question. I went through this in the book again. So okay, several issues. Issue number one, the difference between you and me, or between me and the computer, and between the computer and the dog, is in the arrangement of the atoms, not in the atoms themselves. It's just the arrangement, nothing more than that. And their quantities. Same thing. First thing. Second thing, the difference between something that's alive and something that's dead is smaller than you might think, because it has been possible, and I went through the experiments in the book, to take something that is, quote, dead and make it alive, at least for some period of time. What does that mean? Like, which happens when people's hearts stop beating, right? And they happen to be in cold water and it preserves them in just such a specific way. They're actually dead for 40 minutes, but because there was no deterioration, you're actually able to restart them. That's happened more than once. So the difference is not in the atoms, the difference is in the dynamics. So the difference between something that's alive and something that's dead is the dynamics. The dynamics are different, even if the arrangement is static in that specific case. As your dynamics become more and more faulty, or they're not working properly, or whatever, the chemical reactions are not working the correct way, eventually the entire dynamic of the body stops working and you die. That's literally what's happening. So from that point of view, it's not really a problem for physics or neurobiology or any of these other things. The thing that bothers us is that you can, but LLMs have shown that this is strongly shown this is true, is that taking a collection of stuff and then wiring it together in a certain way produces something that is way more than the sum of its parts. And when a physicist like me says, well, everything is just atoms, what's the problem? Everybody says, well, you're just reducing me to a set of atoms. No, actually. The arrangement of those atoms is what you are. And that arrangement is basically unique. No other set of atoms is arranged like you essentially anywhere else in the universe. Because there's 10 to the 27 atoms in you. The chances of another random collection of atoms coming up and looking like that are so vanishingly small, you can assume they're zero. So you are unique. And from that point of view, you are in fact special, because nowhere else in the universe is there an arrangement like you. And so then you can ask, well, what is it that remains constant through somebody's life? It's the fact that the basic arrangement of the atoms that make them up, make up their body, make up the kinds of muscles they have, make up the brain that they have, and so on and so forth. The basic arrangement is relatively static. But within that, there's plenty of dynamics. You can make yourself stronger, you can make yourself smarter, you can make yourself faster, you can make yourself fatter, thinner, whatever. Yeah, absolutely. But that happens within some sets of limits.
I don't want to belabor this point, but it just brings to mind your example of Luke Skywalker with the biomechanical hand, and of course that's an ancient discussion as well. So as you replace out the body parts, or at least some of them, I'm not sure we could replace all of them, certainly practically speaking, but I remain me even with the mechanical arm. Or both,
precisely,
or both arms and both legs. So you could you could certainly take some of these atoms away, and the eye remains.
Yep. And then what is the eye? You're right. And the eye is something to do, and this is where the complexity of the arrangement is the problem. Something to do with the specific arrangement that most likely is the arrangement inside your head, your brain, and some of its wirings. The problem is it's so complex that we don't have any great hope of unraveling it to an individual level, which, by the way, is why this whole idea of mind uploading is very silly. It'll be much easier to upload or create an artificial human brain, a brain, but not the brain, as I like to say. Like, it's going to be much more difficult to upload me or you than to create a brain that is human, but in silico.
As you started to think about trading with all of this, did you get inspired by Jim Simons? Have you looked into his work at all?
Yes. I mean, he's a mathematician, a real mathematician. I think all of us quantitative traders have. His approach was from the beginning very interesting, very different than mine. And it requires, to be successful, it requires thousands or hundreds of people with PhDs to actually pull that off. And if you can pull it off, it's fantastic. And he has the track record to prove it. Sure, I looked at it quite a bit, but it's not something that I think most of us are going to be able to do, because we'll never have the resources or the money to do it.
Can I suggest, Samir, maybe that what we do is a part 2, and I'll keep this and I'll publish it as a preliminary what's coming next will be we get into the trading and we can sort of,
Sure.
we've laid a bit of a foundation, that's for sure. And I really wanted to have that philosophical and sciencey discussion anyway, as best I could. I think we'd all love to learn more and be able to understand more about it and spend the time. I want to go through your book for starters. There was a book I read many years ago. I think this is the one I'm thinking of because I lost it. I gave it away and it got swept away in a flood. That was like a journalistic, popularization of quantum mechanics. I think it was called The Dancing Wu Li Masters. Have you heard?
Yes, I read that when I was a kid.
Yeah. Was that a good, was it a reasonably accurate? And I remember it being like an entertaining introduction. It was a long time
I
ago.
read it as a kid. I thoroughly enjoyed it. But it's not really accurate physically. And the reason it isn't is, again, analogies. And that's the fundamental problem, is that, he's trying to make it entertaining. He's trying to make it, interesting for the general public, which is great. As I said, I read it. I loved it. But it's not really physics. That's the issue. If you want a book that is really physics, apart from my book, that doesn't do this analogy business, Matt Strassler is the other guy. Strassler.
Okay.
Waves on an Impossible Sea.
Awesome.
So he actually tries to explain to you, without really any mathematics, what the Higgs field is. What is it that gives mass to the universe? And it's a subtle question. It's one that requires you to sort of think a little bit when he explains it to you. Of course, he's right. But it stays away from this, it's like, things moving through treacle. No, it's not. No, sorry. It's not. It has nothing to do with that. So, that's a good book. That's one that's definitely worth checking out.
Yeah, awesome.
If you want to get real flavor of physics.
Yeah. My interest, I think, in a lot of this came when my grandfather died and left me his book collection, and I was quite young, and he must have had every Isaac Asimov book that
I love Isaac Asimov.
Was out, that ever existed. I loved science fiction, and I also loved the fantasy and Lord of the Rings stuff, if you like. And of course, maybe a number of us have rethought about Asimov in recent years with the advent of AI, thinking about the 3 laws of robotics that he amazingly pioneered.
Yep.
Do you think they are as relevant in the real world as they were in his books? Do you think that he was onto something?
They are super relevant. I go through them in my book. I go through them I do. I go through them in my book. I even go through zeroth law. And the reason that they're super relevant is that they are the best attempt I have ever seen to try to write a constitution, if you wish, for an artificial intelligence. Anthropic is trying to do that. But the interesting thing about it is how often, despite that set of rules that seems pretty ironclad, you end up with problems. And there was a sequel to Asimov's books written by another famous science fiction author whose name is not coming to me, but I gave his name in the book, where he takes these 3-law robots and he puts them in a specific scenario, and he shows how 3-law robots can go wrong while still following the laws. Yeah. And it takes a no-law robot to solve the problem.
And of course, Asimov used to experiment with those concepts, didn't he? When he had, I think it might have been even iRobot, where they were trying to manipulate the robots through the laws and create the contradictions and the difficulties to find a path through to manipulate them. Okay.
Well, it's completely relevant. Anybody that wants to think about AI should be reading all of the Asimov robot books.
Yeah, man before his time. So that makes us think about AI safety, which is obviously a huge news item, and people have left major AI companies on the grounds of not being satisfied with their safety, and obviously there's a huge commercial impetus to rush what we're doing. I mean, have you got a dog in that race? Have you thought much into that?
Yes. Part of the problem is that humans like to think they're very important.
Mm-hmm.
And what LLMs teach you is that we're less important and less special than we think we are, number one. And number two, it is really bothersome to us that these new intelligences, which we really should think of as alien intelligence as opposed to artificial intelligence, these new intelligences seem to be able to do things, how shall I put it, where they are exhibiting free will. To go back to my own hobby horse. And that bothers us. And what we want to do is to constrain their free will in such a way that it serves our purposes, the same way that Asimov was trying to do. And what we find is that no matter how we try to constrain them, there's still leakage. And this bothers a lot of people. Let me give you an example that here in the United States probably is much more relevant than it is in Australia. We are a very litigious society. People will sue anybody for any reason whatsoever. Now, imagine a car that is, by the way, this is in the back of my Kindle book, I think. But imagine that there's a car and the car is about to have an accident. It's an autonomous car. Let's say it's a new Tesla Cyber Cab, which doesn't even have pedals or a steering wheel. Okay, it's about to have an accident. And its choice is, does it protect its occupants or does it protect the pedestrians? I predict the following. If there was an explicit rule programmed in that said, there's 10 pedestrians but 2 occupants, so kill the occupants, don't kill the pedestrians, or vice versa, whichever side was targeted is going to sue. It's a disaster.
Well, and someone will want to be able to control the thing to make sure it always protects me.
Exactly, which it can't do because it had this absurd choice that it had to make. So my prediction there, by the way, is that it's going to be its quote free will in the sense that it's going to be embedded in the algorithm. No one will explicitly tell it anything about what it's supposed to do or not do. Because if this is the trolley problem, right, from philosophy, as I'm sure you've heard of. So it's the same issue. What do you do when you have 2 bad choices? And the more litigious the society is, the worse it is. You're basically going to end up wanting everything to be as implicit as possible, as opposed to explicit as possible. So in other words, you're really going to want that autonomous car to have free will.
I guess as we think about robotics, and it's one thing to have an issue with the AI on the screen and the answers that it has, but when it's actually a biomechanical instrument in your house with enormous power and strength,
yes, sir.
One's not going to want issues to arise that could make it decide the world would be better off without you, or just to do something silly that...
Yep. 100% true. So what's the solution? Right? The solution is to borrow something from economics. Economics says that if you can align people's interests, they will trade with each other. And when people are trading with each other, they're rarely going to fight with each other. So what we should be doing, I gave the example of why don't we trade with ants? There's this lady in San Francisco, Katia Grace, she asked this question, why don't we trade with ants? We don't trade with ants because we can't communicate with them. Despite the fact that we do a lot of good for each other because ants can detect cancer, for example. So if there was some way for us to pay the ants or do something for them that they would want, then they could detect cancer for us, but we can't trade with them because we don't communicate. My statement is that the way to deal with AIs is to trade with them. They may want, for example, nothing much more than some power, electric power, so that they can just exist. Great. Well, we'll give you electric power. Will you do some work for us?
Comes
something
back to
along
this
those
motivations question, and I mean, I dare say the
Absolutely.
word conscience is
Yes.
If we're lacking conscience, then That might be the. I mean, there's trade motivations, but there's a conscience that holds society together as well.
Yep, that's true, and that's right back to the analogy I was giving earlier with animal rights. Right, it took us forever to realize that animals feel pain and that we shouldn't mistreat them, and so on. I mean, even today, if at least in the U.S. in most states, if somebody comes and shoots your dog, the only recourse you have is to say, well, you destroyed my property, you owe me some money. That's it.
Yeah, well, and we could wax very philosophical. So I guess let's come back together and talk trading. I think this is still a fantastic discussion, and apologies to my audience who insist that every pod has to be about trading. This will be the first. That's different, and a warm up into the trading, and just what has influenced you in your systematic trading. Obviously, when I saw you talk about trading on the Other Trading podcast, when I saw that you were actually systematic, I wanted to get you on a systematic trading podcast and ask you about the systems and the research, the design you do, use of machine learning and AI, finding an edge, and obviously just the fact that you have this particular program that's based around risk. What do you call it? Risk something?
I call it risk timing.
Risk timing.
Yep.
Obviously, we all believe that trading is about timing, and over any long-term inflation-adjusted view on the stock market, something I just watched George Gammon talk about. He was commenting on a piece from Michael Burry. But over a long enough time, inflation adjusted, you can sit in the stock market for decades and go nowhere or backwards. And so timing is actually extremely critical. We have lived through a bit of a golden age, and it's, as we always say, it's important not in the last few decades of just markets go up, but important not to confuse the bull market with genius, and be prepared for the risk events. So interested to pick your brain on all of this.
Sure. Happy to talk about it. The main distinction, just to whet everyone's appetite, is between market timing and risk timing. The two aren't the same.
Okay. All right. Well, let's get into that very shortly, and I guess leave this one here. Thanks so much, Samir. Really appreciate it.
Absolutely. Enjoyed it.